Great.
You see my screen, right?
Yeah. So today we have pleasure to host Gianluigi, one of us. He will present his recent work on variational autoencoders. Yeah, please take it away.
Thank you. So today we are, I'm going to talk about this recent paper of mine titled CoVAE, Consistently Training of Variational Autoencoders. And just to quickly give an overview of what we are about to see, this is a method to do generation with a generative autoencoder. So what we try to do here is to train a VAE style model with components from consistency models. And the resulting model will be simply a encoder and decoder architecture without a latent model. But we will look more in detail in a bit. So this is what I will cover. First, I will give a motivation of why we decided to work on this project. And then in order to understand the method, we will look at some basics of variational autoencoders, diffusion models, and consistency models. And finally, I will then present the method and some experimental results. If you have questions, please interrupt at any time, or otherwise at some points I will also stop and see if there are some questions. All right, so let's start with the motivation. So diffusion models have recently obtained or somewhat recently obtained state-of-the-art performance in most domains. For example, image generation, but more recently also video generation. This is a video from VO3, and there are many other platforms that can generate very realistic videos and very high quality videos. And they are all based in some way on diffusion models. There is also some attempt at doing text generation with diffusion models, and some very good models are coming out with that. So really diffusions is became the backbone of most generative models that we see now commercially. One downside of diffusion models, though, is that they can be hard to scale because they work in the ambient space, so in the domain of the data. And for example, when you work with very large videos, that can be very computationally intensive, both on training but also in sampling, because diffusion models require this iterative sampling procedure. So one way to overcome this scaling difficulty is latent diffusion. And I think at least the video model that I showed earlier, but also most of the later image models are based on this. What you do in latent diffusion is that you take your data and first pre-train an autoencoder model. So you learn to encode your data and decode it to learn a latent representation of the data. And then once you have trained this autoencoder, you train a diffusion model on the latent space. So the advantage of doing this is that the latent space will be much smaller, and so your method will be faster to train, but most importantly, much faster at sampling. And then what you have to do then is to generate data in latent space, basically bridging your prior to your latent with your model, which is often a diffusion model, and then decode the generated latent to obtain data. And we will look a bit more closely to this in a bit. But so what do we want to do in this project? We have some goals here. The first one is to develop an end-to-end training procedure, which is different from latent diffusion, where you have to first train an autoencoder and then the latent generative model. Then we want to develop a training procedure that is scalable and happens directly in latent space, which means basically getting away from this fact that diffusion models and similar methods are restricted to work in data space, so in ambient space. And then we want to have a method that can do generation in one or few steps. So getting also away from the iterative sampling procedure that comes with diffusion models. Okay, let's see if everything is clear for now. Otherwise, and if it is, we can move on with some background. So I will talk about VAEs, diffusion models, and consistency models because then the method that we proposed takes building blocks from all these methods. Let's start from VAEs very briefly. VAEs are a generative model where you have two networks, an encoder and a decoder. The encoder maps the data to a lower dimensional space, and the decoder does the opposite, so maps your latents to the data space, which is often higher dimensional. And what the encoder does is that it learns a latent distribution, so it doesn't give you just a latent vector, but it gives you the parameters of a latent distribution. In most cases, it's a Gaussian distribution, and then you can sample a latent vector from the distribution and pass it to the decoder and decode this latent to generate your data. So let's look a little bit at the formulas. What you have is a reconstruction loss. So you learn to map the latent back to the original image, and a regularization loss, which is a Kullback-Leibler divergence, which forces the learned distribution to be close to a prior distribution or to match a prior distribution. So in the most simple case, you choose a standard Gaussian, and you regularize your posterior mean and standard deviation to match that distribution. Very importantly, and something that we will reuse later in the talk, is that to sample a latent vector from your posterior distribution, you need to do the reparameterization trick. That's not the only way, but that's the most common way to do this. And it takes this shape. So you have your mean plus standard deviation times the noise. So this is a reparameterized sampling, and that allows your gradients to flow back from the decoder to the encoder. So this works okay as a generative model, but at least in its simplest version, it's known to produce blurry samples. And there are many reasons for this. This has been extensively studied, but in the next slide, I want to show a little bit visually what I think is the main problem with this kind of model. And if we look at a very simple case where you have a one-dimensional posterior distribution, so encoded distribution. So if you want perfect reconstruction of whatever you encode, then the easiest thing to do, for example, for these three data points, x1, x2, and x3, would be to encode delta distributions centered somewhere in this latent space. In that way, the decoder would always know where the sample z come from, because if it's deltas, it can be corresponding to the embedding of x1 or x2 or x3, and can decode it perfectly, or almost perfectly. Now, the problem with that is that after training, your posterior distribution wouldn't cover the whole prior, which, as we said, is usually a standard Gaussian. So we need the cumulative distribution of these three embeddings to recover the Gaussian prior. To do that, you cannot encode delta distributions. You have to encode Gaussian shape distributions. So basically enlarge a little bit, as we see here visually, these posterior distributions. But what happens is that then they have overlap. And when they have overlap, then it's going to be harder for the decoder to distinguish whether a sample comes from the embedding of x1 or the embedding of x2 or x3. And so that in practice will result in a blurriness in your generated samples or in your reconstructions. So that's a little bit the problem that I think, the basic problem really that we have with VAEs. There are many ways to solve it, many attempts to solve it. Let's see, one is, for example, using normalizing flow posterior distributions, or maybe also priors, which allow you to get away from the simple Gaussian distributions and have very complex prior and posterior distributions that seem to improve, but also didn't really solve the problem, maybe due to the instabilities of normalizing flows. Then we have hierarchical models, which have basically latent spaces at different latent resolutions, which becomes a very extensive latent space that also partially improved over standard VAs, but didn't result in in perfect sampling distribution. And the last method I want to mention is the two-stage training, where you first train an autoencoder and then you train a prior over your learned latent distribution. And this was originally done with the VQVAE, but then was also done with diffusion models. So the two-stage training is also equivalent to the latent diffusion method that we mentioned earlier. So this worked very well, the two-stage training, but it requires two training procedures, right? So you first train the autoencoder and then the prior method, which is one of the things that we wanted to get away from. And I have to mention here another paper, which is core-based generative modeling in latent space. What they do there is to train directly an autoencoder and a diffusion model at the same time. So that effectively can do training in one stage. That's good, but then you will still need a diffusion model for sampling. So that gets very close to what we wanted to do in this project, but you still need an iterative sampling in latent space anyways, and two models, encoder and diffusion model. Okay, this was the introduction about VAEs. Now let's quickly look at diffusion models instead. Diffusion models, you train a generative model, very simple way, let's say, by reversing a noising process. So what you usually do is that you define a way to add noise to your data progressively, and then you train a model to remove that noise. Once you have trained that model, then you can start from pure noise and iteratively remove a little bit of noise with the model that you trained until you get to your clean data again. Theoretically, it's a bit more complex than that, but what in practice people do is often to train these models as the noiser network. So you train a neural network to denoise your data at each time step. And then once you have that, there are formulas that show you how you can basically revert from noise to the clean image. But in practice, yes, you have this time-dependent denoiser loss. And the way you add noise to your data, again, this is quite important for our method. The way you add noise to data is usually done this way. You have a linear combination between data and noise, where these AT and BT are scalar factors that progressively remove the influence of the data and increase the influence of the noise. And yeah, the reason why I'm highlighting this is because it's very similar to the reparameterization trick that we saw earlier, but we will look at this again in a bit. And finally, for our method, we have consistency models. They are very similar to diffusion models, but they are designed to do sampling in one or few steps. So you still have the same noising process or forward process that you use in diffusion models, but instead of denoising your images or data at each time step, you learn to map the noisy images to the clean one. Well, I should mention here that this noising process can correspond to a ODE, to an ordinary differential equation. And what they show in this paper is that you train a model to solve this ordinary differential equation or this ODE. So instead of basically denoising, you map your noisy images to the initial conditions of this ODE. So you basically learn an ODE solver with the consistency models, and you have to impose two conditions to make sure that this is a solver. The first one is the initial conditions. So when you are at 0, so that's already your solution, and therefore your model should give you an identity. And then the consistency property, which states that different points on the same ODE trajectory should give the same solution. So whether you apply the model at time t or t prime, it should, if they are on the same ODE trajectory, then they should map to the same initial condition. This is very briefly how consistency models work. Let's look a bit closer now. You can do that in a discrete version or continuous version, but in this work, we will look at the discrete version. In the discrete version, you simply add noise at two different time steps with the same forward process used in diffusion models, so at time t and time r. And then, for example, you have t here, and r is the smallest one, so or t minus delta t. And then you use the prediction at the smaller time step as a target for the biggest time step. And so basically, you are bootstrapping backwards in time the solution of the ODE from smaller time steps to bigger time steps. And of course, this works because you enforce the boundary conditions at x0. And then in practice, for stability, you need to impose this other boundary condition where you have a skip connection between the noisy input and the prediction of the model with two scaling factors. And this is something very similar to what is done in diffusion models as well. And that guarantees stability or improves stability over training. And then, yes, your loss is simply a squared loss between prediction at smaller time step and prediction at bigger time step. So to wrap up, we have VAEs that have this encoding procedure and makes generative models with that very simply using these two architecture, encoder and decoder. Then you have diffusion models, which have noising process, and then iterative denoising with this average denoiser loss. And then consistency models, which is very similar to diffusion models, but instead of doing the average denoising, you always predict what the solution is at the previous time step, so that you, instead of having an average denoiser, you have an ODE solver. Okay, let's now look at some similarities between VAEs, diffusion models, and consistency models. Before that, are there any questions or something that wasn't clear?
There was on the last slide, previous slide.
Yes.
There was theta minus. Does it mean that it's fixed, like you're not doing backpropagation on it?
Exactly. Yes. Maybe I could have explained this better, but let's look at the previous image. Basically, let's say now we are in discrete consistency models, and you have these 4 discretization steps. When the first time is 0, that's the boundary condition here. So there is an identity. There is no prediction from the model, and it's used as a target for xt. But then when you select, for example, xt and xt prime, the prediction at xt is used as a target for xt prime. So there is no backpropagation on the prediction for xt, and that's what's written here. So the prediction at the smaller time step is used as a target for the bigger time step, and there is the stop grad operation on the smallest time step, so that the gradients are only backpropagated through the bigger time step.
So this is something that is known as bootstrapping, and it's famous for its role in reinforcement learning. The idea is that you only have the true loss at the boundary condition, which is at equal to 0, and then you kind of move the loss backward by using your model as proxy loss.
Yeah, exactly. Okay, this is good to stress it, because then we will reuse it in our method. So it's good that this part is clear.
Just quick question. So is it possible that can create accumulation of errors?
Yes, it does, and also can be unstable. So now I just laid out the very basics of training consistency models, but in practice you need a lot of tricks, especially in the earlier methods. For example, you start with pre-trained with weights of a pre-trained diffusion model, or you need these boundary conditions here, which greatly increase stability. Then you need, for example, to have a schedule on the discretization step. So you start with the very coarse discretization, a few steps, and then progressively increase discretization steps to get almost to the continuous case. So these are a lot of tricks really to improve stability. So yeah, because as you said, you can accumulate error, but also you could your model could diverge. So then yeah, then it's generally hard to train consistency models, especially in their earlier versions.
Right.
Okay, but thank you for the questions. Let's for now move on. So again, let's check at some analogies between VAE diffusion models and consistency models, which will then naturally lead us to the intuition of this of our method. So here we have a few diagrams that show diffusion models, consistency models, and our method, which is a little bit giving away what we're going to do. But basically, this red line shows a little bit the forward process of diffusion model, and the blue line is the model, and the purple now is the loss. And you have similar inconsistency models, while for our case that we named CoVAE, this line is dashed and yellow, which symbolizes an encoder. So it's not in ambient space, it's in latent space, and the green line is the decoder. But for now, let's look at our first analogy. So assume we only have one time step t. So in VAEs, of course, there is no time step, so that doesn't really count. But for diffusion and consistency, we have a whole range of time steps from 0 to the maximum time step t, big T. For now, let's assume we only have one. Let's say we have T1, okay? Then turns out that diffusion model and consistency model losses are identical to the VAE reconstruction loss. What does this mean? Is that for a diffusion model, we would take x1 and always map it to match x or x0 with a denoiser loss. And in consistency models would be the same, because in the discrete case, we would only have one discretization step. And as sorry, my mouse is in the way, okay. For consistency models, if we only have one discretization step, you would always map your noisy state x1 or x1 to the initial condition, right? So the diffusion loss and the consistency loss in this example in which we only have one time step are the same. So it's a denoiser loss from a small time step. And it also turns out that it's the same as a VAE reconstruction loss, because maybe let's look at some formulas. In the diffusion loss and consistency loss, you have your forward process at this unique time step t, and your prediction is matched to your input x0. In VAEs, you have one encoding of x, and we sample z from that encoding, and then we map that latent space to x. So you have a denoiser loss or decoder loss in both cases. And again, here it's important to stress that the forward kernel used in consistency and diffusion models is equivalent in some way to the reparameterization trick, with the difference that in diffusion model, AT and BT are scalars, while in VAE, the mean and the standard deviations are nonlinear functions of x that also don't preserve the data dimensionality. But the remaining of the formula is the same. And in theory, you could use complex functions for AT and BT, even though they would still be dimensionality preserving. But yeah, so this was the first analogy that I wanted to show. Again, with one time step, the losses are identical, and the reparameterization trick is very similar to the forward process from diffusion models and consistency models. Now let's look at the second analogy. Let's assume now that we move away from this one time step condition, and instead we have a time-dependent VAE. The time dependence here can be enforced with a beta parameter. A beta parameter is didn't mention it earlier, but you can regularize your VAE with a beta scalar to control how Gaussian is your latent approximation. So for small betas, you will have delta distributions or latent distributions that are not close to Gaussians at all. And for very big beta, you will have almost Gaussian distributions. So in this analogy here, what I propose is that we can extend a VAE with a time conditioning and introduce a regularization of beta, time-dependent beta regularization that increases beta with time, so that for small times you would have almost no Kerr regularization, and for big times you would have almost perfect regularization, so almost perfect Gaussian. What would happen there is that for a diffusion model, so now we have again our arbitrary time. For diffusion model, you have the standard diffusion model loss as we are used to. For VAEs, you have then a time-dependent reparameterization trick, and you always have a decoder loss, which is also time-dependent. So now we can look again at this graph. For small t, you will be able to decode almost perfectly your latent because the beta regularization is small. For big T's, the beta regularization is very strong, so we'll have almost Gaussians, and you will have a blurry reconstruction, or at extreme case, a reconstruction that reverts to the average of your data set, like happens to diffusion models when you are at very big time step t. So this is not very useful right now, this time-dependent VAE model, but what I wanted to show with this analogy is that, first of all, if you regularize properly with this time-dependent beta, you obtain something that resembles the forward process in latent space. So you have a latent space that transitions from delta distributions to full Gaussian distributions. And the second thing is that, yes, if you then train this VAE naively with this decoder loss, you get something that looks very similar to a diffusion model loss. But the only difference is that you have a mapping from latent to data rather than staying in the data space. Okay, and so these were the two analogies that I wanted to mention before going to the method, but I guess now it's clear, or you can guess what the next step is. Rather than training this time-dependent VAE with the denoiser or decoder loss like diffusion, we can then train it with a consistency loss. So instead of always mapping to the initial data X, you can map to the prediction of the previous time step, so that you can obtain a consistency model in latent space. But let's look at it now in the next slide. Until now, everything clear? Can I move on, or are there some parts that we should talk about more?
Maybe just a quick question on that.
Yes.
So, you're basically enforcing at the same time in the reconstruction loss the forward process at the same time. So you're doing this. The second term is, so what is not clear maybe is why all the time the KL between the latent encoder, the time-dependent one, should also always match the prior.
Yes, but the beta tells you how much, basically, or how much importance to give to the reconstruction loss as opposed to the KL regularization. So basically, yeah, with a smaller beta, you really prioritize the reconstruction loss, while with a big beta, you prioritize the KL. Was that what you asked?
Yeah, I think it's clear.
Okay, thank you. Okay, but then let's look at CoVAE, and here is what the method consists like. CoVAE stands for consistency training of variational autoencoders, and it consists in training variational autoencoders like they were consistency models. So in this graph, we see an encoder, time-dependent encoder, that thanks to the beta regularization, encodes your data into something that looks like a delta distribution for small time steps, and that progressively transitions to full Gaussian. So a little intermediate time step will be Gaussians, but not fully centered, maybe, or something. So basically transitioning to Gaussians, and then as t grows, you will have basically indistinguishable latent distribution, or almost indistinguishable latent distribution for all your encoded data. And then, rather than decoding and trying to reconstruct always the input data, we will do a decoding at a smaller time step. Here is dashed to show that we don't take gradients here, like in consistency models, and then use this as a target for the decoding at the bigger time step. And the intuition here is that we leverage the fact that we have a latent ODE. So this time-dependent encoding, if it's regularized properly, implicitly learns a latent ODE. Therefore, we can use consistency models techniques to learn the solution to this latent ODE. But the decoder here will not only decode. So we don't have two models here. The decoder will be both decoder and consistency model. So the decoder will both learn the latent ODE solution and decoding of this solution in one step. So you don't have two separate models, one for the solution and one for the decoding. But again, the only models, the only parts with parameters are an encoder and a decoder, like in standard VAEs. So that's CoVAE. Let's say in practice, we can do that in two ways. Option one, as I mentioned earlier, we can have our consistency-like objective where we decode at time t, which is bigger, and time r, which is smaller, without backpropagating gradients, and our time-dependent beta regularization to ensure that these latent transitions from point masses to Gaussians with a reparameterization trick that is, as we saw earlier. So our time-dependent mean and time-dependent standard deviation latent space, both for T and R. And then we have option two, which is a little bit simpler, where you can still have the same reconstruction loss, but you can have a encoder which is not time-dependent. So you always encode at Z0, and then you can do a forward process in latent space at time t and at time r. So your time-dependent encoder would be basically the combination of encoding plus latent forward process. These are both valid. Let me see. The first option is a bit more complex because you have to tune beta t properly. So it's a bit harder to deal with, and you lose some properties, for example, knowing the SNR at each step of your latent forward process, while option two is much easier, less hyperparameters, and a bit more clarity on what happens in the latent space. However, in our experiments, we found that option one worked better. So in the remaining of the presentation, I will keep going on with the option one. In the paper, we have a section on option two, which worked a little worse, but I think it's still relevant to know that this option exists, and maybe with some more work, we can also scale this up to get good results. Now, one thing that I mentioned earlier also was highlighted thanks to the questions, is that consistency models can be very hard to train. They can be unstable, you can have error accumulation, and so on. So in standard consistency models, use this reparameterization that we saw earlier, was introduced in diffusion models in EDM. And you have two scaling factors, C-skip and C-out, that at 0, C-skip is 1 and C-out is 0, so that you have your identity function. Therefore, you respect the initial condition for consistency models. And then as T increases, the contribution of C-skip decreases and C-out gets closer to 1. This is also done to preserve some quantities, let's say, so to have stable training in general. But one problem with this in our setting is that xt lives in here. Xt lives in ambient space for consistency models, and also the prediction of the consistency model lives in ambient space. In our case, that's not possible because xt is instead zt, so it's a latent variable. And in most cases, if not all the interesting cases, zt has a lower dimension than xt. So we cannot directly apply these boundary conditions because zt lives in a lower dimensional space. However, this
it's not only interesting. It's not only interesting in lower dimension. I mean, plenty of applications but regardless, it's a different
dimensions. Yeah, like of course, when you use hierarchical models, zt would be much higher dimensional. That's true. That's also an interesting case, but perhaps then different dimension than xt, right?
But at least differently structured, right? Like in stable diffusion, I think it's more or less the same, but of course they have very different structure and very different meaning, so they wouldn't mix together.
Yeah, well, in latent diffusion, they are generally smaller. Yeah,
I don't think it's true. Is it true? Like
in latent diffusion,
Gabriel, because Gabriel did work with it. I think Gabriel was the one telling me that in the current stable diffusion model, it's basically the same.
Right, as in, but the shape is different. Is that what you mean?
The shape is different.
Oh, right, yeah, like as in they compress the spatial resolution but increase channels. Yeah. So okay, yes, but generally, at least the shape is not exactly the same, or at least they have different meanings. So in any case, the case in which zt is exactly the same dimension as the input is just not that common or very uncommon. So in most cases, this EDM boundary condition is not available.
Yeah, and again, even if it were, it would be mixing apples and oranges. One is a latent space representation and the other is a visible. So even if it's the same dimension by coincidence, it's still not a good idea.
Yeah.
But I'm confused there. So because I thought you also meant xt to be the latency or not?
Yes. However, in now for simplicity, let's say that xt is your
input.
It's the noisy version of the data when you use the diffusion forward process, right? While we call zt our noisy latent, even though it doesn't really mean much in this case, but zt is the encoded latent at time t. So xt is the one used when you use a simple forward process from diffusion or consistency, and zt instead is obtained when you have the time-dependent encoding and the reparameterization trick. So in this case, yes, xt would have the same dimensions of x0, and the prediction also has the same dimension of the data. While
it's basically because you're using the same denoiser or as the decoder, right? So
well, this line here, it's a simple consistency model, right?
But so, in your setting, you said that you are using the same network to do the denoiser and the decoder.
Okay. Exactly. So in our case, we have a latent data, and then our decoder would be placed instead of f, but zt would have a different dimension than the decoder output, but also different dimension than the data that then we want to model. So we would have a mismatch in dimensions. Okay, but the boundary, of course, thank you. But the boundary conditions are seem to be very important for stability. So in this work, we propose to use a different style of boundary condition, which means that we need to learn yet another quantity. So instead of using xt, which is the noisy version at time t for the standard for processes, here we learn to model the average denoiser like it would be in a simple time-dependent VIE, the one that we saw earlier in one of the analogies. And we use that instead of xt plus a network that predicts the residual between that average denoiser and the actual target. Let's look at this a bit more closely. Why we think this makes sense? The first reason is that for small t, the average decoder should model pretty well the target, right? Because there is not much noise and it should be quite straightforward. Like, for small t, the decoder loss should be close enough to the actual target. For big T, of course, this should be just a blurry, messy reconstruction, but then we can control the effect of these two quantities with C-skip and C-out. So C-skip at small t would be mostly recovering the average decoder, which is a good approximation, or if not correct. And then as t increases, we decrease the effect of the average decoder and we increase the effect of the residual prediction until it basically only matters the residual prediction, which then becomes a residual of 0. So it becomes the actual consistency prediction.
I have a question. Can I ask one question?
Yes.
I'm not sure in the consistency model, but in EDM, for example, they use the C in and C noise.
Yes.
To allow stable training to make sure that the variance is 1.
Mm-hmm.
Do you also use that in consistency, or did you think about using that in the input of the networks?
Yeah. So that's more a technical detail, but yes, in consistency models, it's usually used, both C noise and C in, depending on the forward process you use. In this specific instance of CoVAE, I didn't use it because you don't have a good notion of what
the forward process.
Exactly, of what the forward process does. In the second version, the one that I showed that is a bit simpler, then there we could use the same components. But what I experienced empirically is that the magnitude of the latent doesn't vary too much over T. So it seems like the network learns a relatively well-behaved latent space, let's say. So of course, being able to do that would probably result in improved results, but for this method, I didn't explore that further.
Okay. Yeah, I think it's good for maybe feature work.
Yeah, exactly. Okay, but again, so here we have this different boundary condition, and just to show how we parameterize this decoder average decoder network, instead of having a separate network, we simply double the channels of the last decoder layer, so that half of the channels are used as average decoder, half of the channels are used as average consistency, as a residual or consistency model, basically. The reason why we do this is that usually consistency models are initialized with pre-trained weights of diffusion models, which are trained with the denoiser loss. So we assume that there is a certain degree of compatibility between the diffusion features and the consistency features, and it ended up working relatively well. In practice, of course, also another step for future work, if we want to still use this formulation, is to investigate how compatible the features are and maybe branch out the network to different levels. But with this parameterization, it was very cheap to do that, and it worked quite well. So we decided to stick to this for this work. Okay, let's look at a little bit of pseudocode before moving forward. This is basically very similar to discrete consistency models pseudocode. So we have a discretization schedule that changes as training iterations proceed. So we will have a very coarse discretization step in the beginning and a fine-grained one as training proceeds. We sample data from the data set, 2 time steps based on the time step distribution, which in this case I always use uniform distribution. A uniform in the discretization steps, yes. And then sample noise. We do the forward process or the latent forward process at both time step T and time step R. So it simply means that we do 2 different encodings conditions on T and R. And then we compute the CoVAE loss, which is the output at R as a target minus the target at T needs to match the target at R. And then we have the denoiser loss. So part of the denoiser of the decoder is trained as a denoiser, and maybe we can look again. Sorry, here you see D is the total output, but just training big D wouldn't mean that the average decoder part is trained. So we need to add this additional average decoder loss. And finally, the time-dependent KL divergence. To ensure that this latent space transitions to Gaussian, so that it resembles a latent ODE. And that's, the total loss is L CoVAE plus L denoiser plus LKL with some scaling factors to adjust the strength of each loss. Let's now look at sampling. This is very simple because we have our trained decoder and encoder. If we want to do one-step sampling, we simply sample noise from the prior and then do the decoder for the biggest time step that we have. And this is exactly like you would sample from a VAE. You sample noise, decode. So that's one-step sampling, and it's similar to consistency models, but here the difference is that epsilon is in latent space. If you want to do multi-step sampling, we have a similar procedure than consistency models. In consistency models, you would re-noise your generated data with the forward process at a smaller time step, in this case tau n, and then reapply the consistency at that intermediate state. Here we do something similar. After we have decoded our initial noise and we have one sample, we can re-encode that sample at intermediate time step and resample noise for doing another reparameterization trick, and then re-decoding that latent sample to generate again. So we have basically a procedure for one-step sampling and multi-step sampling that we can use, similar to consistency models, basically. Okay, that was a little bit of an introduction of the whole method. Are there any questions for now, or something that should be clarified?
I had one question. Can you hear me?
Yes, of course.
In the pseudocode, you mentioned that do you always take the biggest tau?
Or in the sampling?
Yeah.
Yes, for the first step, yes. So what you would do in the consistency models, for example, if you have time that goes from 0 to 1 and 1 corresponds to pure noise, then you would do the first sample or the first forward pass using pure noise and 1, that is your biggest time step, right? Because that's the time at which you obtain pure noise in your forward process. And the same we do here. So here we have some hyperparameters, but basically sigma max is the biggest time step, and that's usually where the model is trained with noise, with pure noise during training, right?
Have you looked at least qualitatively what images look like if you take like a tau that's in between, so not the max, but somewhere in between? Do you still get decent looking images?
That's a good question. I haven't explicitly tried that. I think you should still get something looks like an image, but generally they don't look that good. So what happens here is that we have to regularize with the sigma max is something that I have to choose, because we have to make sure that the regularization, the beta regularization at this value results in a Gaussian latent space. Doesn't mean that each encoded variable has to be Gaussian, but the cumulative distribution of our posterior encodings has to be Gaussian, right? So what happens is that if during training I was to set this too small, the latent wouldn't reach Gaussianity by this value, and therefore you would have a bit, I don't know how to describe them, but they don't look that realistic. You start to have a lot of artifacts in these samples, while increasing sigma max further, at some point there is no more benefit in further increasing it, which means that you've reached enough Gaussianity in your latent space. So yeah, but I guess to answer your question is that yes, if you use a smaller one, you would get a lot of artifacts because yeah, the model wasn't trained with that distribution at that time step.
I have one question.
Yes,
So
of course.
wait, can you go back where you split your neural network into two outputs?
Yes. Here.
Yeah. So you're training them together. Like you have special laws for only S, and then
Yes.
special laws for like combination of S and R. Like for
Yes. Yes, correct. And good that you asked because I didn't mention this, but in this formula, S also received stop grad.
Okay.
So I forgot to put the minus here, but in the output of the decoder, so if we look at the pseudocode, in this loss, the gradients only flow through R.
R. Okay. Yeah.
Here, which is the same as the consistency model in standard consistency.
Okay, yeah.
And then we need the extra score-like or the core VAE-like loss to make sure that this quantity is actually the average decoder.
Okay, yeah. Yeah, because I thought maybe that what you could do is like just first train S.
Say again?
Just train S part. So you using this loss for S, and then do something like LoRa to fine tune S to from S to get R, and then combine them, and then you just train R separately.
Yeah.
Because I don't know how.
That's a very good suggestion, actually. And that's something that I think is worth exploring in the future. But the reason why I did it like this, because one of the goals was to have this end-to-end training procedure, right?
Yeah.
So one of my constraints that I imposed to myself for this project was to just find a way to do this end-to-end. But yeah, that's a very good suggestion.
How those two losses combine, like which one is stronger? That's why I thought that maybe it was.
Yeah, no, that's in fact there are scaling factors, right? And these are also somewhat empirical because in this formulation we don't have a clear understanding of the SNR. At least we don't have an analytic formulation for that. But I played a little bit around with reducing the effect of the score loss at bigger time steps so that it wouldn't interfere with the consistency loss. And there were some small improvements by doing that. So it is definitely like this is definitely not the final and best way of doing this, but it was a good partial solution at least to get the model to be more stable. Because yeah, without this, the model would diverge very easily.
Yeah. Thanks.
And I mean, the two losses could help each other, right? Because it's a lot of features will be in common.
Yeah, that's true. But again, then it's about, for example, yeah, for small time steps, definitely. For bigger time steps, it could be that the quarter loss gets too big, maybe. So it is true that there is some subtleties to think about here. But yeah, also I think it was good enough first attempt at solving this.
Yeah, of course, for bigger time step, the score loss becomes high variance and uninformative. So then it could mess up a bit training, and that's something maybe could be fine-tuned.
Yeah. Okay. For now, let's look at the experimental results, and then at the end, we always have time to go back to more questions. So the first experiment that I want to show is that it's a latent space analysis on a MNIST. So this was not to get the best possible results, but rather to see what happens in practice when we use our framework. So the first plot that we see here is a TSNE embedding of our latent for different time steps. So we train CoVAE on a MNIST with the smallest time step 0.05 and biggest time step 3. And by the way, it's important to stress that time in CoVAE is only, it's is not explicit time as in diffusion models or consistency models. It's implicitly enforcing a beta regularization. So there is no actual concept of time, but we still use t as an indication of how strong the regularization is. Anyway,
This would
so
be quite
yeah.
interesting. Of course, it sounds a bit difficult to actually do, but if we could get the entropy profile here, it would be quite interesting because it will allow us to actually reconstruct what time actually is under the hood.
Yeah, maybe you can do the post-training. Probably.
If we have the score, right? Because you're doing score training. If we have the score, essentially we can. If we have the score, we can reconstruct the time axis.
Yeah, or
Assuming
again, we can always revert to the simpler formulation. That's much easier because you have the explicit time there, right? So, but yeah, also for this one, we could find
I really
ways.
like the kind of innovation of your formulation, like in which it's really a beta by that is implicitly creating the forward process. I don't know, conceptually I find it very interesting, and it's nice to see that it actually works better. Yeah,
and also with this formulation, you actually learn for each data, for each dimension, how to sort of add noise in a latent space. It doesn't really make sense said like this, but you learn how much to keep and discard on your latent space with the encoder, so it's much more flexible than the standard forward processes. But anyways, this plot shows samples from latent spaces at different time steps. Okay, and we have the TSNE embedding of this sample, so the latent was actually 49 dimensional or something like that. This is the 2D projection. And what we see is that the colors here are the classes. So, for example, the purple is 4, the orange is 1, and so on. And what we see is that these clusters are first I would say very well separated from each other. And as time progresses, they get closer and then more meshed with each other until you can very barely distinguish them. There, you can maybe see, if we zoom in, a little bit of clusters inside, which is fine, because what we said is that the cumulative distribution should be Gaussian, not each single distribution. So it's okay if some information is retained, but this confirms that our beta regularization is effective, right? To transition from very distinguishable latent spaces to almost indistinguishable ones. And then to further confirm this, or to get a visual understanding of what happens, these are input images at 0 and a 1, and this is the latents at different time steps. What I show here is the latent mean, latent standard deviation, a sample from the latent distribution, and the noise mask used for that sample. And the noise mask will be the same in each row. So for each time step. So this row has the same noise mask, and this row has a different noise mask. The reason why I put this here is because for small time steps, the standard deviation will be almost 0. What it means is that the latent sample or the latent reparameterization trick will give you something very, very close to the mean. So the noise information here is almost disregarded. And the mean will look like some sort of compression or latent version of your input image. You can see here 0 shape and a 1 shape. As time increases, there will still be similarity with the mean, but you can start to see, maybe if we zoom in a little bit, some more characteristics from the noise being added to your latent. And as we get as we get to the biggest time step, you can barely notice any similarity with the mean, while your latent sample will be almost identical to the noise, to the latent noise. So this also further confirms that our beta regularization is effectively creating some sort of latent forward process. And the last plot that I wanted to show is this. We computed the latent signal to noise ratio after we trained the model, and that on the same interval between 0.05 and 3. And we also here see that goes from very, very big at 0.05, which means almost only signal, to very, very, very low at 3, which means almost only noise. So this slide was mostly to show that the behavior makes sense in a way, or that we can achieve what we wanted to achieve. So this latent forward process. And now we can look at some results. This is a simple toy problem where I just train a MNIST compared to an equivalent VIE and equivalent beta VIE. The beta VIE was tuned on some values, and this I took the best, and it's evaluated on FID. And we see how of course, the beta VIE improves both in generation and reconstruction over the VIE, but CoVAE significantly improves over both on one-step generation. The two-step generation further improves performance, and we can also have a very good reconstruction, because if we encode and decode at the smallest time step, then the model will be very good at reconstructing that.
So this is a very nice thing, I think, to think a bit about, right? That essentially in VIE you have this trade-off between encoding in a sharp way, like Gianluigi showed, and covering the prior. And if you encode very sharp, you get very good reconstruction, but then you cover the prior very poorly, and the other way around. And now with Gianluigi's formulation, with CoVAE here, we have that since we have multiple time points, we have essentially multiple noise levels, and then you can achieve these two goals at the same time, because you will achieve very good reconstruction at low noise level and very good prior covering, basically effortless at high noise level.
Yes, but also important to stress that with a VIE, you also have very good prior covering, especially if you have a very big beta, but then your samples will be blurry.
Yep.
While in CoVAE, with the consistency loss, we can bootstrap the signal from low time steps to the big ones where you cover the prior effectively. So that's a key insight of our method. And also, I think it's important to stress that in this instance, the model is exactly the same. So we have exactly the same parameters, exactly the same architecture. Just by changing the training procedure with this time conditioning, we can achieve much improved performance.
Yeah.
Okay, now let's look at the, there is a little ablation on C410, just to show a little bit how changing some components changes the performance. The green one corresponds to the same settings. So if you see it in different histograms, it's exactly the same run. The first one is FID versus latent size. So here we see how, increasing the latent size improves FID. And I think this is an active area of research, which is given an autoencoder, how can we compress more? And so with this simple architecture, it was a simple UNet without skip connections between different resolutions. The compression rate is not that good, but yeah, so in our experiments, then we decided to stay with a 3-time compression rate. Then perhaps, increase performance with batch size and model parameter. Batch size, bigger batch size usually reduces variance, which is great for consistency models. Usually they need very big batch sizes. And of course, increasing model parameters also helps quite a lot here. And the last was an ablation on different losses. So the first two use L2 loss and pseudo-Huber loss. Pseudo-Huber is let's say it's a interpolation between L1 and L2 that is commonly used in consistency models. So the first two columns here, I was just using it on the simple loss without boundary condition, and pseudo-Huber would diverge at some point, while L2 would work, but not that good. And then when you see the combination, we have L2, for example, or in this case, L2 for the score loss or the denoiser loss, and pseudo-Huber for the consistency loss. And here we see how with the same settings, using the L2 for the decoder loss and pseudo-Huber for consistency loss is the best working combination and achieves substantially better performance. All right, now some results compared also to other models. So there are methods, of course, that work way better than this, especially diffusion methods or methods that use several sampling steps or distillation methods and so on. For this comparison, though, I chose to use VAE-based models. So we have NVAE, which is this big hierarchical model, which has been state-of-the-art autoencoder for many years. And then we have DCVAE, which is another VAE, which is trained with adversarial loss and I can't come up with a name, but contrastive loss, yes. And that also was a state-of-the-art VAE before our method, I would say. And then there are some other VAEs, but those are generally latent models. So you have first a VAE and then generative prior. So I decided to not include them here. In the paper, there is an extensive discussion about all these methods. But anyways, on CIFAR-10, which is a very common benchmark for image generation, we have the usual VAE and beta VAE, which have the same exact architecture as our model. And you can see they perform relatively bad. And then we have NVAE and DC VAE, which improve quite a lot and start to get very good generative results. CoVAE, this is the first version of our method without an adversarial loss. And we can see that already using that improves over all the baselines, especially over DCVAE, which does use an adversarial loss. And we have very good first and 1 and 2 step generative performance, but also achieve overall best reconstruction FID.
Yeah. Just note that DCVAE is a nice FID, but the reconstruction is horrendous. Just to point out.
So the DCVAE seems to get away from the the adversarial loss dominates over the VAE loss, because then the reconstruction loss gets very bad.
So if you notice, like for all VAEs, the reconstruction loss is lower. The reconstruction FID is lower than the generation, for the obvious reason that it's just easier to it's just easier to get good images by encoding and decoding than by sampling from scratch. While DCVAE acts like a gun, so it actually gets good generation but doesn't give you good encoding. So I feel it's a bit more of a gun than a VAE, and that explains the kind of high performance and generation.
Yeah, and then final row, our best model, CoVAE with an adversarial loss, which is commonly used in the recent VAEs. And yeah, that gets best FID overall over all these methods. So very good here. And then another benchmarks on CeleBay 64. Also here, now I only compared with the NVAE and DCVAE. And also here we get overall best performance, and it's not shown in this presentation, but in the paper, again, there is a more extensive comparison, and this performance gets very close also to some of the methods that use two-stage training procedures or complex priors distributions and so on. So that's very encouraging result. And again, this is all 1-step and 2-step generative performances from decoder without any trained prior.
So the comparison with NVAE is quite interesting, because NVAE is a much larger architecture, much more complex architecture on latent space. So actually it would be quite interesting to try to drop the NVAE. The nice thing is that essentially CoVAE is you can just drop the CoVAE learning scheme in an existing VAE architectures almost off the shelf. You need to change slightly the output channels, but almost off the shelf essentially. So it will be quite interesting to apply to NVAE and see what performance we can get, because really the architecture we use here are really not that complex.
Yeah.
Is it true that, for example, if you perform the NVAE, all the steps, right, because it's a hierarchical VAE, maybe it's going to give you better performance, but so this is the reason it fails to?
The NVAE does perform all the steps, as in it does decode at each hierarchical level already. So yeah.
But this is 1 step. Do you mean it does the whole chain or not?
Yeah, but it's not like a diffusion model. So it's a 1-step generative model also on the NVAE, but you have sampling at different resolutions from the latents, let's say. So yeah.
It's an orthogonal axis. It's not about the diffusion step.
Yeah, but maybe do you require to do more number of function evaluations, or?
NVAE by design can only do 1. So you cannot really do multiple in VA.
Okay.
Yeah.
Thanks.
Of course. Okay, I think that's almost there for the presentation.
I have a question.
Right. Yeah, of course.
So have you tried more steps? Like how does the curve, FAD curve looks like?
Yes, that's so with more steps, you still get a little bit of improvement. There is a table in the appendix of the paper. It's, yeah, you lose benefit, I would say, after 3. Already 2, it's good, but after 2, you get a very small margin, and 4, you still get improvement sometimes. But I would say, yeah, yeah, two steps seem to be the biggest gain here. Yeah.
Thanks.
Of course.
Oh, I also had a question. How come the NVAE doesn't have a reconstruction loss?
Oh, this was not reported. They do have reconstruction loss. I haven't found it reported on some other papers. Yeah, but they do have reconstruction loss, and my guess is that it's very close to this number, if not similar. Yeah. Let's look at another result here. This is more qualitative. It's a VAE, so we can do latent manipulation, and with the CoVAE, you get some attributes of your images. So we can basically aggregate some encodings that share the same feature. Oh no, sorry, this is a different one. Never mind. Then manipulation, yes. Here we interpolate the latent spaces with different linear factors, and we do the decoding. So since we have this time-dependent encoding, we can do this at different time steps. So on the left and right, you have the original images. The first column is on the left, and on the right is the reconstruction, pure reconstruction of that. And you see that for t equals 0.05, it's almost identical, if not identical. And then as we move towards the center, there is an interpolation with the image on the right-hand side. So for small time steps, if the images are relatively similar, you can see how the transition is quite smooth between one and the other. If the images tend to be quite different, there is not very smooth transition and seems to be more overlap between the 2 original images. And that also respects or is in line with the beta VAE functionality of disentanglement, right? For small beta, you don't have very good disentanglements, but good reconstruction. For big betas, you have bad reconstruction and good disentanglement. And that's also what we observe here a little bit, that as we increase T, the reconstruction is less faithful to the original image, but you have more smooth transitions until we are at the biggest T, in which you retain very little of your original image. But yeah, there seems to be much more smooth transition between the 2 latent spaces. So
what's about this big leaps in high time?
Yeah, because here in this experiment, I use always the same noise mask for all these images.
Okay.
So it seems like that noise mask at big images is associated with these big leaps. So then they all tend to get that characteristic. But it's good that you asked, because yeah, it's not a characteristic of the model, but rather of that specific noise mask that I used in this experiment. But yeah, that was just to show that there is latent manipulation capabilities. The fact that we have multiple time steps makes it a bit more ambiguous, or you need to a little bit find the time step that works for your needs. What I was mentioning earlier is this manipulation, as in adding or removing attributes, and there is a section about that in the paper. But yeah, being an autoencoder does open the door for manipulation in latent space. Okay, I have a last slide for conclusions, and then we can take a few more questions if you guys have still time. So it's an effective end-to-end VAE-based generative model. That's the main conclusion. It's not yet at the performance of the state-of-the-art generative models, but it is a state-of-the-art VAE model with this end-to-end training procedure. So that's, I think, a good achievement for this project, and then there is room for improvement. Again, let's go through the positive parts. We managed to stay within the one-stage training procedure from scratch, so everyone can take this model and train it without the need of a pre-trained model or without the need of multiple training stages and so on. We gain the interpretable and lower dimensional later representations, which is usually inherent in VAEs, and it is better than other VAEs with similar settings. So negative parts of this work is that at least with this formulation that we used, you have loads of hyperparameters. You have to choose the beta schedule, the weighting schedule for the loss term, the discretization steps, minimum and maximum T, and so on. So there is really a bit of overhead in terms of how many hyperparameters you need to get this to work well. And future work is some future directions is to simplify the whole training procedure. Part of these hyperparameters, though, come from the consistency model training procedure. So also there, if now I chose one specific baseline for consistency models, if you switch to more advanced ones, maybe you can get away with less hyperparameters or a simpler training procedure. And then another con is that it's not yet on pair with other state-of-the-art generative models. So if you were to choose tomorrow a generative model for a product, probably you wouldn't pick this one. But I think the results are encouraging, and I will definitely keep working on this to try to scale it and make it work much better.
And I mean, again, like the benefits here is not necessary. I mean, this is trying to really compete with VAEs, right? And we need to keep in mind that VAEs are highly used at the moment in the context of latent diffusion. And I think is where, besides, of course, there could be progress that are made compatible with regular consistency model. But I do imagine that if we drop this model at intermediate noise levels on a latent diffusion setup, we could substantially increase the performance of latent diffusion. Without making just with the model as it is now, without making major improvements, because it's going to be substantially better than the VAE. It can also rely on one-step generation, from the latent space. So that's and then you can use intermediate noise levels because anyway the diffusion model will learn the prior, so it doesn't need to be fully Gaussianized. So I think that's very exciting. And if I had when I will have the bandwidth to put someone on it, I would definitely want to do it because it's again, that's a big deal, right? You try and improve stable diffusion or latent diffusion models, and especially in the area of video generation, you really want to perform this kind of compression. So having good compression models can really make a big difference.
Yeah, that's true. Yeah, so also again, playing with the VA architecture and the other components that will also be direction for future work. Okay, I think that was it for the slides. So now we have time for more comments, questions, and discussion.
I didn't quite understand the part about it being more useful for latent diffusion because the one-step thing is the same as the current encoders they use, right?
Yeah, but the performance is much higher. So
yeah, I mean,
just
go ahead.
Yeah, no, that I do think considering that the performance is much higher than the regular VAE, we could just take VAE training, add, of course, it needs to be calibrated, right? Making this consistency-based model work is a bit of a pain, and it always needs a bit of time for calibration. And in a large-scale setting like in Stable Diffusion, it will take a few months to just get everything work correctly. But essentially, when we're done, then we get the encoder-decoder model that is much more powerful than what we currently have. And having a good encoder-decoder can unlock a lot of power in the diffusion model underneath,
Okay. Then I have another question, because at the very start you mentioned two possible formulations for the loss function, but the second loss function doesn't talk about the beta term at all, right?
Yeah.
So
yes.
In that case, I'm kind of confused how you do the bootstrapping.
Yes, that's a good question. So the second formulation doesn't need a beta, and it's much simpler. but also loses some power, right? And it's maybe now a good point to dive a bit deeper in this, because in the first formulation, you have a fully learned latent forward process, but you need a beta regularization to get it to actually be a forward process. But what it means is that you can learn how much to retain about the input and how much uncertainty you have about the input, or let's say how much to trade off between input and the latent input and noise. And also you can change the shape of the noise based on the input. So what you have is a latent forward process that adapts to your input, but also adapts your noise to the input. So you also introduce some sort of coupling. That's a lot of flexibility compared to standard forward processes. But the downside is that, yes, you lose analytical tractability, so you don't have an explicit formulation of SNR, at least during training and other quantities, and you need to introduce this beta regularization. So that's the price to pay for this more powerful formulation. On the other hand, what you can do is to simply encode X to Z0. So without time, basically, this encoding is you never add noise to this, and at the smallest time step, you basically just want to decode it. And the deal here is to regularize this properly. So of course, if you have a completely free-form encoder, this can take any shape, and then it won't make for a good latent space. There are some tricks, for example, normalization and tanh, which is now commonly used on autoencoders to make sure that this Z0 that you learn is in a reasonable range. And then you can apply forward processes like in consistency and diffusion, but directly in latent space. And by doing this, you already have guaranteed that you will have a latent forward process, because at 0, you will have 0, and at big T, which is maybe 1 or whatever sigma max, you will have pure noise, like in consistency and flow matching models. So this is great because you then have all your analytical quantities that you can wish for, like in every diffusion and flow matching model. You are guaranteed to reach noise at big T or at the final time step, and you don't need a beta regularization. But you lose in flexibility because now, again, you don't have any sort of coupling, you don't have any sort of custom forward process for each data, and so on. Does that answer your question?
Yeah, thank you.
Thanks.
One question, Gianluigi, first, thanks for your nice presentation. I was thinking that if you maybe analyze or have any intuition about, because in a stable diffusion, you have these two-stage processes, where they focus first in having a good reconstruction encoder, right? So they minimize the reconstruction that you show in your experiments. But do you have an intuition of what would be the challenges if you want to scale this to something like stable diffusion end-to-end? Because there's also these like latent consistency models, right? That they use these pre-trained encoders that are trained using an adversarial loss.
Yeah.
But I guess if you do it end-to-end, then it's a bit more challenging to make sure that you have a very good encoder, right?
That's true. Yes. So that's a very good point. I guess this formulation has some advantage and some disadvantage compared to these, for example, latent consistency models that you mentioned. The advantage or the disadvantage of CoVAE is, yes, that you have to do everything in one go. When you pre-train autoencoders, the latest versions like DC, deep compression autoencoder, so DCAE, they do a 3-stage training procedure for the encoder, where they first train the encoding and decoding, then they fine-tune some layers, and then they add an adversarial loss on top. With that, they can achieve much, much bigger compression rate. But yeah, the training procedure is harder, and therefore combining that with an end-to-end training procedure of also the generative part, like we do here, can be tricky, and that can become problematic in practice. So what I'm trying to say is that, yes, having a performant autoencoder and generative model at the same time is not trivial to do, at least in one step. However, one good thing of this method is that you never have to worry of your latent space. So in latent consistency models, at least in some of these works, they show that you cannot simply reuse the same losses that you use in consistency models, because your latent embeddings have different outliers, have different range, and so on. So you need, they propose, like as in consistency models, you use pseudo overloss. In some version of latent consistency models, you need to use different modified losses to get it to work well. In CoVAE, you never work in latent space, at least when it comes to decoding. So you always work in data space. So you can reuse more building blocks of what works for image models, for example, because your loss for the decoder will be, again, in image space. So that's a good advantage in a way.
And do you have any intuition? Because I think this approach has the potential, to solve that problem. But of course, maybe, I mean, the bottleneck is how to improve the encoding while also having a good consistency model at the same time.
Yeah. So my insight is that the training procedure of consistency models can be very unstable. So if one could directly improve that, then the benefits would translate already in this model, because the consistency model part is a problem, on the side, right? And if you can improve that training procedure, then you can get much easier times when training CoVAE. That's one stage, and the other one is the encoder. Yes, sorry, not the encoder, but the decoder. So the encoder is relatively okay to train most of the times, but when you want to compress a lot, seems like, I mean, this is still active RF research, so I don't have a final answer to this, but seems like having an adversarial loss can help the decoder making up details that are not present in the latent. So when you compress a lot, you cannot have all the details on the image, and so that adversarial loss encourages the model to come out with these details, basically. Again, I'm not sure if this is the actual truth. I would love it if there was at some point a procedure for very good autoencoders with very good compression rate that just uses L2, for example, or simple losses. But yeah, for now it seems like that's not possible. So yeah, having or improving the decoder training and having it combined with the consistency training can be another step for getting better results.
Thank you.
Okay. Do we have more questions? Comments? Ideas? All right. But then if yes, Darren?
No, I would say like if that's it, we can thank you for doing nice stuff.
Thank you all for
attending and
for the
great job.
questions. Thanks.